All right, so let's take a look at example 2. Here we have another implicit function, right? We have some equation where where one variable is not expressed explicitly in terms of the other, right? So now we're told that this represents a rotated ellipse. And we want to find the points at which the ellipse crosses the x-axis. That's our first problem. And so just remember that the x-intercepts occur when y equals 0. So we want to set y equals 0 and solve for x. So let's just do that. So we have x squared plus x times 0, so that won't be anything, and then 0 squared, so we're just going to get a couple of zeros there, and that's equal to 3. So x squared equals 3. So that's telling us that x is equal to the plus or minus square root of 3. Okay, so our x-intercepts are the square root of 3 comma 0 and negative square root 3 comma 0. All right, so those are our two x-intercepts. And now the next part just asks, show that the tangent lines at these x-intercepts are parallel. Okay, so what do we know about parallel lines? Parallel lines have to have the same slope, right? And the slope is the delta y over delta x, or for a curve, the instantaneous rate of change of of y with respect to x, right? So we want dy dx. So again, I don't want to solve this for y in terms of x to get dy dx. So I'm going to use implicit differentiation to do this. So let's just differentiate the equation as it is and treat y as a function of x. Okay, so the first term is just 2x. So when we differentiate that, we're going to get, sorry, the first term is x squared. So when we differentiate that, we're going to get 2x. All right. The second term is a product. All right. So we need to use the product rule on this one. We've got x times y. All right. We're going to use the product rule. So it's a derivative of the first, which is just 1. Right. I could write 1 times the second, which is y, plus the first, x, times the derivative of the second, which is dy dx. Okay, so this whole thing right here is the derivative of that second term, xy, right? I'm just using the product rule on it. And then finally, we've got the last term, which is y squared. So here we have to use the chain rule. So we got 2y, right? The derivative of the outside function, times the derivative of the inside function, which is dy dx. Okay, and that's equal to 0. All right, so now we have to rearrange this equation so that we can solve for dy dx. So let's see, we want to group all these dy dx terms together. So I'm just going to leave them on the left-hand side, and we'll have x dy dx plus 2y dy dx, and then we'll move all the other terms to the other side. So we're going to get minus 2x minus y. Okay, and then we can factor the dy dx out. So we're going to get dy dx times x plus 2y equals minus 2x minus y. And then finally, we'll just divide both sides by the x plus 2y. So we get dy dx is equal to minus 2x minus y over x plus 2y. All right, so there's our derivative. And now we want to find the slope at these 2 points that we found in part A. So let's do that over here. So dy, let's kind of draw a line maybe. So dy dx at let's start with square root 3 comma 0. If I plug in those values, I'm going to get, so I get minus 2 square root 3 plus 0, right, over the square root 3 plus 0. Okay, because y is 0. All right, and then I can reduce that to a minus 2. And then let's look at the derivative at the other point. So we have dy dx. We want to find the slope of the function at minus square root 3, comma 0. All right, so I'm just going to again put the values in. I'm going to get, so in this case, I'm going to get 2 square root 3, right, because I got minus 2 times minus square root 3, over minus square root 3. So, and again, my square root 3's will cancel, just like they did up here, and I get minus 2. So, those two, the derivative of each of those slope, or sorry, the slope at each of those points is the same, which means, so the slopes are the same, so the lines are parallel. Slopes are the same. So the tangent lines, I should say, the tangent lines are parallel. All right, there you go.